Today's talk is on x86 disassembler internals. Basically, it's about how disassemblers work, focusing on the x86 instruction set. I'm Richard Johnson. I work for iDefense Labs. I also do some research with the No Login Research Group and the Uninformed Research Journal. iDefense, if you don't know, is a company that does a lot of vulnerability research and has a program where we purchase security research from individuals like yourselves. We can talk about that later. But purpose of this talk is to basically introduce the core components of a disassembler, refresh some binary format parsing concepts, explore programmatic disassembly analysis methods, as in writing your own code to do your own disassembly. And hopefully, at the end of this, you'll be inspired to take on the task of developing your own binary analysis tools and disassembly tools as well. Basic layout's going to be a discussion of the core architecture, followed by some basic disassembly analysis methods, including some code examples. And then we'll talk about some more advanced stuff, including methods for path analysis, such as loop detection and data flow analysis through various methods, whether it be static or emulation-based. So, disassemblers, they basically are used to decode machine language back into a human-readable form so that we can read the code at a very low level after the compilers produced an output form from a high-level language. Reverse engineering has been around forever in many different forms, but in the software world, we use a program, disassembler, to understand an unknown or closed system that may not be open source or may not have sufficient documentation for us to understand the algorithms and the inner workings of that program or protocol. Reverse engineering has a number of applications, whether it be interoperability. There's people who reverse engineer on OS X, for example, or on open source platforms to create software that's compatible with iTunes or other proprietary formats. Copyright evasion, of course, some people started their reverse engineering and cracking software, technology theft, and software security, finding vulnerabilities. The goal of reverse engineering is generally to gain a higher level understanding of something that you don't have much information about. And the low-level disassembler is powerful, but it's very limited in an instruction decoder in the sense of, it's powerful because it gives us a readable representation of code, but it doesn't really do a lot of work for us off the bat. So it's a pretty tedious process to manually comment all your code and manually discover every little bit of functionality from a line-by-line assembly representation. Some more advanced disassemblers, such as IDA and HTE, Bastard from Mammon, they're capable of doing a little bit more work for us. They can understand the format of various binary executables. They can detect function prologues and calls to locations in code. They can do some cross-referencing on static data locations and code references of immediate values. And I'm about to show you that now we can take it a little bit further and also recognize structures and objects in code, which is a very useful capability when you're dealing with an unknown piece of code and you don't understand how the data is represented within that program as it gets processed and flows through the program. So the core architecture of a disassembler essentially involves an instruction decoder that is essentially described in an architecture manual, the mnemonic representation of the actual machine code opcodes that are produced by the compiler. And so you can read these manuals and understand the lookup tables that you need to create. And so when you go through parsing the binary code, you perform these lookups and decode the instruction opcodes and then the operands and the flags, and we'll take a look at that here in a second. In addition, the more basic functionality of parsing file formats is pretty crucial, so you can pull symbol information and understand where static data is kept in the file and where text data is kept in the file. So maybe you can be intelligent about how you represent that data in your disassembler. So real quick, IA32 is just considered to be a more complex type of processor. Its instruction set is a little more complicated. There's variable ways to do the same task. Rather than only have a add instruction, they have an add and a multiply and a divide. There's multiple methods to create the same functionality within the processor itself. RISC architectures tend to be a little bit easier to write disassemblers for. They have a reduced number of instructions and therefore generally only have one table to process, as opposed to in an Intel instruction set, you have multiple length opcodes. So whether it be 1 byte, 2 byte opcode, 3 byte opcode, you're gonna have different tables, and you just have to do a little more parsing. It's not a lot of work programmatically, but more so in building the tables and just having more flags to process. So this is kind of what a typical disassembler's internal tables might look like for decoding an instruction from byte form back into the mnemonic. Essentially, this, like I said, there will be multiple tables. This one is the 1 byte opcodes, and they're just indexed by their hex value into this table. And so you'll see that opcode 0 or 1 or 2 looks like it's going to be an add, and then following that you see these two columns, the ones beginning with AM underscore. Those are opcode operand value flags rather, and below these defines kind of describe what those operand flags mean and how you process the operand from the bytes that are following the original opcode that you're actually decoding. So in the case of an add instruction, you're going to have two values following it. It may be a register, it may be an immediate value, and depending on whether it's going to be a register or immediate value, you're going to have a different opcode, and the flags are going to be different for the operands. So I mean, it's pretty straightforward. It's just a lot of table lookups and continually looping through this processing. And yeah, so to break it down a little bit, you parse the opcode prefix by first looking at the first byte of the instruction that you're currently on and decoding. Multi-byte opcodes will still have, of course, the first byte being one of 0 through 255, and depending on which one it is, there will be significant opcodes that say, okay, well this one is actually the beginning of a 2-byte opcode or a 3-byte opcode. So you determine which table you're going to do your opcode lookup in, and then actually just straightforward index by the opcode number. And then you parse the addressing method of the operands, whether it be register, immediate, or displacement value from another register, and the size or type of the data that it's going to be using in that opcode. So the two primary executable binary formats that we deal with, or maybe three now, if you want to include OSX, so would be ELF on Unix platforms. Most Unix platforms support ELF these days. PE file format, or PE-COF, would be the standard Windows file format, and Mach-O would be the OSX file format. I'm going to give some pretty detailed information on how to process each of these PE and ELF binary formats, but I'm going to kind of skip over it a little bit because I've added a lot of content to the latter portion of these slides. So we'll get a brief overview of the executable formats, and then you can look at the actual code samples in the slides later to get a better idea of how you parse symbols. But all executable binary formats have certain properties in common. Their purpose is to tell an operating environment how to load and possibly link this file into the running operating system so that you can take it from a binary image into a process image and allow it to execute by setting up memory segments and relocating symbols and so on. So the kernel and the userland actually have two different views of a binary. The kernel understands it as a series of memory segments that need to be initialized with different permissions, whether it be a readable and executable segment or a writable segment for data, etc. And for dynamically linked binaries, there's an interpreter in userland that performs the runtime linking phase, which actually allows you to use shared libraries and fix up the import tables, whether they be the PLT or GOT in ELF or the actual import tables in the PE file format. And the linker views the file a little bit differently. Rather than simply understanding that there are memory segments with different permissions, it understands that there's significance to certain types of data within that file. There's various sections. Some sections hold symbols. Some sections hold, again, static data. Of course, the text section holds the actual code of your program. And so the linker itself usually parses a certain set of sections to understand which imports are going to be required and what relocations are going to be required to finalize the process of allowing this program to execute from beginning to end. So ELF, it's been around quite a while. Like I said, I'm going to kind of skip over this a little bit, but it was originally in Server 4 Unix in 1989. And it includes all the significant information I just mentioned, section headers, symbol tables, string tables, dynamic linking information. And when we're writing disassemblers and code analysis tools, binary analysis tools, it's important that we retrieve as much of the information that's there as possible and use it in cross-referencing and use it in contextual hinting and stuff when you're actually displaying that binary. So just real briefly, ELF objects are composed of an ELF header, which defines the overall structure of the file. It has pointers into where the program header table is, which is what the kernel will interpret as the memory layout information, and also section header tables, which is what the linker will interpret for its various fix-ups and relocations. And then, of course, object code and specific symbol tables. And then the ELF header looks like this. As I said, I'm not going to go into too much detail here, but it essentially tells the operating system at load time what this file has been output for what type of system, and whether or not it's appropriate to be running on this particular operating system. Basically, in the kernel, your ELF loader, or all your binary loaders are actually in a linked list, and it goes through a kind of a drop-through system to do some checking if this header at the very beginning of the file is describing a file that's supposed to be processed by this particular function. And if not, it'll return it and it'll go back to the next one. And that's why you have the magic OX7F ELF at the very beginning of it, so it can check the magic header on that as well. Then the section header table begins simply by taking the base address of the mapped ELF file and adding the ELF section header offset value, which is part of that ELF header we just saw. And the sections are described through this structure right here, which has a symbolic name, significant types, flags, the load address, the file offset, etc. And again, I have a lot of code in here. This is essentially code that will allow you to process this, but I have example code too, so we'll kind of go over this part of the code a little bit later. PE, of course, has the same significant information that tells the operating system how to load it as well. It's a little bit more of a cumbersome to parse. It's not quite as straightforward as ELF, where it's typically an ELF. You basically take the base address plus an offset to whether it be a section header table or the program header table, and you multiply it by the number of the index of the section header that you want to address. Whereas in PE COF, you tend to have to follow a more indirect path to actually get those offsets that you're looking for, because it actually is composed of multiple different little types of file formats, including a DOS stub that runs in native 16-bit mode. It includes a COF file header, which, funny enough, has things like pointers to a symbol table, which is not actually used in PE COF. It's a conglomeration of a few different file formats over the years, and it just ends up being a little more of a pain to deal with. But let's see. So the final component of a disassembler that's going to be useful to reverse engineer is going to be the disassembly analyzer. And this is where really a lot of the work comes in and takes that parsing capability and turns it into a representation, doing some work to tie all these symbols together within the code references, and is capable of actually bringing meaning to what all this readily available information that's there means to us. And it does this by parsing all the information, building a database, and then as it represents, as it displays this to you, as it outputs it to you, it'll continuously be doing lookups in its own database of, is this a symbol that we know? If it is, maybe we should display the symbolic name rather than just the address. It's much more meaningful to us. It's pretty immature area. It's definitely an imperfect science. You can, you can do a lot of programmatic analysis on a file, but you're never 100% sure of the accuracy of that analysis, because there's many tricks that can be used to defeat debuggers and disassemblers, and we'll take a look at a couple of those as well. But the more powerful it becomes, you start to draw the line between static analysis and how much of this code you're actually trying to emulate or run to determine the actual outcome of a certain code path, or if you're trying to do data reference tracking, you're actually building a huge tree of references, and it's almost like rather than worrying about the actual value of what that is, you're worried about who's touched the same types of memory locations. So you end up emulating a lot of work and doing a lot of computation behind the scenes. And as you do that, it becomes closer to true emulation or execution as opposed to static analysis. So let's take a little deeper look at what types of information you should get from the basic disassembly analyzer. These are the functionalities that we already expect out of something like an IDA Pro or a more advanced disassembler. They should include things like function detection, static data references, string references, understanding execution branches and where a call came from or where a jump came from or where it's going to. That's very simple. It's, as long as it's using immediate values, 80% at least is pretty readily available to a disassembler that just has a little bit of logic for tying this stuff together. And then in addition, something that we don't see a lot of is disassemblers that have like advanced hinting for us. Things where maybe it'll make comments about what it guesses a chunk of code does, or maybe it understands system headers like WinDebug, understands Windows objects very well, and you can output a structure format of anywhere in memory. Well, we don't really have a disassembler that can say, I understand that this is using this object and this is what it looks like, except for IDA. IDA is pretty good about understanding that this API call takes this data object and this is what it looks like as values are being passed to it. That should be a standard feature, though. It's not difficult to parse header files and understand, the objects that are actually inside a compiled binary, if that information is available. And then, things like on Unix system calls and, all this information is static. It just simply needs to be collected and parsed and then just built into this knowledge database that a disassembler already has. So function detection is one of the more basic analysis tasks. It's actually quite trivial. Basically, in most standard compiled binaries that include function prologues, there's a standard method of doing a function prologue. In the case of standard C, it's usually push EBP and move ESP to EBP. That's just basically storing your frames so that you have a new frame of reference for this function. When you push stack variables and whatnot, you're actually kind of closed off in your own local context. So that's what the purpose of a function prologue is. In some cases, it also does things like initializing stack canaries, or maybe if you have some function-based packer, it will do its packing and unpacking or encrypting in the function prologue as well. And Microsoft actually, in Visual Studio, has now modified the function prologue a little bit. I thought I'd point it out. They've added a move EDI in front of the push EBP and move ESP EBP. And they've also included 5 no-ops prior to the function prologue. And this is in all system libraries and system drivers for Windows. And basically what it allows you to do is it allows you to apply trampolines elegantly without having to overwrite a couple of bytes of the actual beginning of that function. So essentially, you would overwrite the move EDI with a jump backwards 5 bytes. And then in that jump backwards 5 bytes, a relative jump is actually 5 bytes as well. So you create a backwards jump and then a forwards jump to anywhere in the code that you want. That's a way to do a trampoline. But it's just that there's very standard prologues, so you can detect these in code. In the case where there aren't function prologues, where they omit the frame pointer and they don't keep frames, they base variable references off of the stack pointer rather than the frame pointer. You can just look at the call destination. So when we parse through code and we see that it's calling to a certain address in the code, well, a call means that it's going to push the stack pointer, or the current code location prior to making that call. So you're making a functional context switch. So you can treat those the same as a function that would have already had a frame initializer at the beginning as well. And in the case of disassembler, if there's no symbolic name from a symbol table, then it's pretty standard to assign it something like sub underscore and the address of the code location. And later you can go back and rename that. But just initial understanding. And then here, this is actually some text that's taken from a disassembler I wrote. I'm going to be releasing that today. And it shows cross-references of where this function was being called from. And that's just, it makes for easy navigation and quick referencing within the code. Let's see. Oh, I believe I went backwards. Here we go. So as we build this database of where the functions are and where these code locations are, we begin to see these cross-references that are determined by examining the immediate or evaluated immediate operand values, meaning like an actual static valid address, or an evaluated address if we're capable of following through a few instructions and we see that they've moved an address to a register and maybe they've added an offset to it or something. That's not overly complicated. But the point is that if you can understand the destination of a call, then you can create this cross-reference and these symbolic representations. And the one thing, though, that is required to actually track cross-referencing well is the inclusion of permissions flags within a disassembler instruction decoder. So these would be things that would signify this operand reads from the other operand, or this operand writes the other operand, since we don't really have to, or in that way we don't have to actually keep another table of, well, all adds work in this way, they read from one, write to the other, or all jumps work in this way, they execute operand one. So if you include these flags within that, it's easily parsed and makes for good cross-referencing. Well, there's only 2 libraries that I'm aware of that are open source and available you can use right now, one being libdasm, which is written by JT, who has his code posted on nologin.org, and then the other would be libdisassem by Mammon, which also includes the cross-referencing capability. And as you're parsing the operands for the cross-references that might be produced by each line of assembly, there's various types of operands, immediate, memory, and register, as well as displacement, et cetera. And depending on how complicated your operand evaluator is, if it can determine these relative offsets or not, you actualize that value to a memory address and then do your lookups based upon that. So there's basically code execution flow and data flow that we're going to be concerned with. Code execution flow is going to give us a graph of possible destinations within the code from various code blocks and what all the paths are through the code. And those can be determined through 3 basic assembly flow control instructions: calls, branches, and returns. And they can just be analyzed for functionality and creating this tree. As far as data associations, you're going to be looking more for the symbols, strings, and pointers within pre-initialized data. And if you get into emulation, then you can also look at pointers within heap allocated data or runtime allocated data as well. But you can see here, I have the cross-reference at the top is obviously a code cross-reference. In the 4th line there, the move shows from the address 402000. That's going to be the data section within a PE file. And so that just shows that this is a pre-initialized string. We know what that is. We know it's a static offset. And then the next line is a call printf, which we have the symbolic name for since that's a shared library symbol. And finally, to get back to hinting, system call hinting is a pretty obvious one. We know the syntax of system calls. We know that most system calls take their arguments in the registers, which makes it pretty easy to determine what the register state is at the execution of an int 80. And it's a matter of parsing a simple kernel header file and just building, again, those structures within the database. And every time you hit an int 80, then you just look at register state and you determine which values have been passed into EAX, EBX, et cetera, and are able to enumerate the arguments to that system call. And then again, the parsing of default library header files and possible open source shared library include files as well. And then you can even go as far as doing something like kind of heuristic function call argument detection. I did this in dltrace, which was a bit of a hack, but it was a dynamic shared library call tracer, and it basically analyzed a program in this method here to essentially determine at which offsets within a function it was referencing argument values that were passed and local variables that were passed. And then depending on the size of that reference, it would determine, is it referencing a word size value or a d-word size value? Is it dereferencing it within the code? Is it a pointer? Does that pointer evaluate to something that points to ASCII data? Doing a simple, is it 4 bytes of ASCII text in a row? Well, if it is, why not show that at runtime as a string value? Well, this can be done very similarly in the static analysis point of view, where you can also simply analyze the arguments based upon their offsets from EBP or ESP, depending on if they're using frames, and determine how many arguments there are and how those arguments are being used within the program as well. And IDA represents this through naming arguments like arg0 through argn, whatever it may be. So, in my opinion, I think most of the features described here are fairly basic. It's mostly cross-referencing of known data. And there's only a few disassemblers available right now that do implement at least 4 out of 5 of these features, and that would be IDA, HDE, which is a great cross-platform visual console disassembler, the Bastard, which has gone through a couple of development phases. I think it's currently going through another rewrite, but quite powerful library. And then Codis, which is the tool that I wrote. And I'll give you a little demo here. It took me about 2 weeks or so, maybe 3 weeks, to kind of get this working to the stage that we have it now. And it's capable of parsing both PE and ELF. Let's see, I guess this is actually pretty small. All right, let me see what I can do about that. Is that a little sort of better? All right, we'll try it. So anyways, I have an ELF file and an exe file here. Codis has a few options. It's not like a super functional disassembler, but it can do AT&T and Intel format parsing, or format representation. It can show the hex bytes if you find that useful. It can dump symbols, only show the headers, etc. So we're going to go ahead and just check it out on an ELF file first. Is there any way we can fix this? I'm sorry?
Could you move the screen a bit to the right?
Yeah, they have it expanded a little bit. Here, let me see.
Can you maybe switch the light on?
Yeah, I'm fine if we want to dim the lights real quick. I don't know if that'll help here. Basically, it shows at the top here, it's detected 4 main sections that it's going to be dealing with here as executable sections it's going to disassemble. The other ones it treats as data because in the section header, flags are set to only be readable and writable as opposed to executable. So that's a very simple way to determine if code is going to be executable. It reads the file header as an ELF, a 32-bit ELF file, which is little endian, and evaluates the entry point in the file size. And the first section in an ELF file is typically a null section, so that's why you see, or maybe don't see, a it's actually getting brighter up here, I think. Okay, well, I hope maybe some of you can see this at least, but basically by default, Codis will provide a hex dump of data sections, as you can see here. And when it gets to an actual executable section, you will see that, here we go. This is the PLT section, which is where all your dynamic symbols right here on the left you can see are being resolved through the symbol table lookups and relocated. Of course, this is where most of your cross-references are going to be within the code for dynamic symbol calls, or dynamic function calls, rather. Let's see if I can find the text section. Okay, so and here's the text section. Same deal, cross-references, temporary names on detected functions. There should be some jump cross-references as well in here. Symbols obviously are being resolved. So it's a semi-useful console disassembler, but basically I wrote it as beginning code that if anybody else wants to kind of build their own disassembly tools, they can begin with a small code base. It's about, I think, 3,000 lines maybe. and it includes the binary format parsing for both ELF and PE, includes the kind of a bit of a modular instruction decoder, so later you could plug in things like PowerPC. Yes, do we have a question? No?
What language is it written in?
It's
like
in
ANSI, C, or?
Yeah, it's ANSI-C.
Okay.
And it compiles in Cygwin and, of course, under GCC on Linux. It's actually pretty portable code. It should compile without much effort, even if you wanted to switch it over to Visual Studio as well. But yeah, so I mean, it's a good start. It's basically, you could develop a UI layer for this. You could make it interactive and jump around. It's just some good demonstration code that comes. Oh man. All right. That's used to demonstrate the initial disassembly analysis features that I was just discussing. So let's talk about a little more advanced topics. What can we do once we already have this program database built of the internal references, and how can we do a higher level analysis that will actually benefit a reverse engineer or other programmatic analysis tools in gaining a deeper understanding of how the code works. One of the best ways to prototype more advanced disassembly analysis concepts is through using IDAPRO's SDK. I'm actually a pretty recent, I have pretty recent experience with IDA, its SDK on a plugin development front, but it's actually quite useful. Some of the documentation's a little sparse in some places, but in general, it's very usable, and IDA obviously is something that's familiar to most people who are professional reverse engineers at this time. It's by far considered the most usable disassembler and most flexible for multiple reasons. But so to take the idea of path analysis and data analysis a little bit further, I'm going to give two examples. One being Peter Silberman's loop detection plugin, which he released in the Uninformed Research Journal last issue, and a little tool that I've been working on recently that allows you to enumerate these structures within code and track references as far deep into the code as you need to. And we'll take a look at how that works. But path analyzers essentially are going to need to understand how the control flow graph looks like and recursively follow the execution flow in order to build this graph and determine all possible code paths within a specific binary. And we can group these paths by understanding which shared library calls or which sets of functionality are being dealt with within a specific code path. For example, if we're looking at a binary on Windows that's a FTP server or something, or an IMAP client, and you're looking for a specific command within that protocol and how it gets parsed, well, you simply go to where it parses the input. It will do some comparisons on if this is a, whether it be a GET command or a POST command in HTTP, arbitrary protocol. But once it determines that, and then you just look at the code flow after it's made that decision of how to treat this specific request, and you can group that functionality together. So that's the most obvious use of a control flow graph, is understanding which parts of the code do which parts of the work. And then disassemblers that don't have this ability would be linear disassemblers, and they can't determine the relationship of code blocks. That would be, Codis currently actually does not do a complete control flow graph analysis. Object dump would be the most familiar one probably to, that just does a straight linear disassembly. And here's the problem with that. Handwritten or custom assembly code can actually cause disassemblers to go awry when they're doing linear disassembly, and you don't really understand what the code's actually doing. So here's something I just wrote up really quick. It's kind of a silly example, but so we have a function right here called loc, and it just pushes a value, and then it jumps backwards 2 bytes back into the actual value it pushed. In this case, that's EBFE, which is the opcode for jump backwards 1. So it's basically going into an infinite loop. Well, our disassembler doesn't show that at all. Our disassembler basically shows that, oh, it's going to do a jump, and it's going to do some more pushes, and it's going to move, and it's going to return from the function. In reality, when you actually execute this, obviously, it goes into an infinite loop, and you never reach that code below it. So that's the most obvious drawback of a linear disassembler, is you're not guaranteed to understand the actual execution path if it doesn't actually follow these jumps. And this jump right here is what I was talking about earlier, where a code flow control gets diverted, and you need to take note of that and understand that if it gets diverted, where is it getting diverted to, and in this case, you would be able to detect that it's getting diverted back into itself infinitely. So IDA builds these control flow graphs, and this is what the default output of one of their control flow graphs would look like. It's just, you obviously can see the possible data pass below the calc function here. And this is every bit of code that you need to look at within that program if you want to know exactly what calc does. Well, when we look a little bit further into control flow, one of the most common high-level constructs that we see in most programming languages are some form of loops, whether it be a for statement or a while statement or some form of understanding loops and continual execution of a piece of code for a certain length of time. And in order to speed up programmatic analysis, sometimes it's better to understand where these loops occur and understand that you only need to parse the specific section so many times, or understand that since a loop is occurring here and perhaps it's performing some string copy operation or a stircat or something along those lines, a loop is occurring and it's taking user data. Perhaps this is a location we should look at for vulnerabilities because loops are common areas where people make mathematical mistakes and the counts of the number of times you can loop, etc. And so let's take a little deeper look at Peter Silverman's loop detection plugin. Basically, there's two general types of loops, reducible and irreducible, and these are categorized in such a way that when you look at the control flow graph and you understand that there are pathways between two nodes in that control flow graph, that sometimes those pathways are inconsequential and they're not actually part of a loop. In this case, it's best demonstrated where B and D call back and forth into each other. There's a pathway between those two, but our actual loop is going through A to B to C to D and back to B. So a natural loop is that A to B to C to D, and we want to figure out how to eliminate the possibility that that B and D should be treated as a loop, because it's actually not. It's just a reference back into the higher function. Maybe it just jumps prior to where it was. And the more complex ones are demonstrated by this one down here on the right, where there's multiple interesting pathways, and it's much less obvious of what the direct flow is in the loop that's demonstrated here. And those are called irreducible loops because there isn't a head node like the B here that can be determined as the only way to go through the loop that's represented in the second graph. But using IDA's cross-referencing, Peter's managed to develop something that can take an example, such as the one we just saw, and determine that this one does contain a loop, and that one over there, although it looks as though it has a loop and there are code paths, it does not actually contain a loop that would be interesting for software vulnerability discovery, or it's an insignificant relationship back and forth between the code locations. So we understood that execution flow analysis is generally determined by creating a graph of all possible code locations and then abstracting a little bit, observing how those paths can be taken within the code. But data analysis is a little bit more difficult because references into data, or references to data, are typically passed in registers, and they're highly variable. They may come from unknown sources. They may not be from within the file itself. So there's a number of obstacles to actually trace assembly for data reference tracking. And as far as I know, prior to my most recent research, I hadn't really seen a very good working implementation. There were a couple. There was like an ObjRec plugin, I believe, that was developed by Halvar for IDA. I had some trouble getting that working. I think there was a couple other attempts at it, but they were very initial and seemed to be a little bit flaky. So I thought about this problem quite a bit and how I would approach it, first from a static analysis perspective of how you would do variable tracing without understanding what the information was, but simply understanding the relationships between the code and when references were being made to a prior reference of a specific instance of data. So you would begin this by creating a cross-reference, a specific reference at the line of code that you want to begin tracing at. And this would be where a register or a memory location would be assigned that actual data that you're looking to trace. Following this, you would have to go through each instruction and attempt to actualize the operand values at each line to determine if these were pointing to prior references based upon what was in your tree. And so I kind of have a little, thanks to Matt Miller, he gave me a little assistance with MS Paint, and we have a little bit of a diagram here. So you would start to create these, this tree of references in the code, and when a reference was invalidated because that reference had been overwritten, you have to worry about cleaning up all the other references that were still pointing back to that original memory location or register. And so if you see here that if you were to invalidate the red block there on the right, then you would simply have to worry about invalidating the blue block that follows that. But as you get more complex relationships, you see higher up, then you have to worry about invalidating and tracking the relationship between all of the nodes that have been referenced all along the way. So you end up taking a whole lot of memory and creating these very complex tree structures of references to references from within the code and understanding how to clean up all of your references when one becomes invalidated. And this can kind of be described as a combinatorial explosion scenario on large pieces of code. If you restrict it to smaller portions of code, it's more applicable, but essentially, this occurs when a huge number of possible combinations are created by increasing the number of entities which can be combined, forcing us to consider a constrained set of possibilities. It's a whole mouthful there, but essentially just means that you're going to run out of system resources before long if you're going about creating all these complex trees of relationships between data references in the code. So my approach of this was actually to take a look at using emulation rather than pure static analysis. And emulation solves a lot of the problems that we see with this because you can immediately actualize what the data references are. And if you're emulating memory allocation calls, in the case, which is what I do with IDA x86 EMU, then you can actually just create boundaries within memory and watch for references from those operands that you're able to actualize to the pointer values. And so if they get dereferenced and that dereferencing occurs within the memory boundaries that you've set up to watch as structures or objects, then you begin to understand that those references are actually members of a structure or object that you're following. So as I mentioned, IDA x86 EMU is an emulator that Chris Eagle wrote and Jeremy Cooper as well. And it's kind of early in the stages of development, but I found that Chris is really easy to work with, and he's actually made a bunch of commits to the CVS within the last couple of weeks because I was working with it and we were kind of going back and forth on a few features that might have helped it work a bit better. But one of the cooler features is that it can hook the PE imports and actually load libraries, so you can trace all the way through a program without any real complexity. You basically just start anywhere in the program, and if it's going to call a shared library, it'll go ahead and load that shared library for you. And it emulates the heap allocation calls like heap alloc and virtual alloc, etc., so that we can create these memory references ourselves, give the return value an address that we're tracking within the heap structure that's within the x86 emulator, and then watch for the references to that. And I have a demo coming up here for that as well. This is actually the code of IDA struct, but I think we're kind of short on time, so I'm going to kind of go ahead and get to the demo here. This is the end result over here on the right. Essentially, you begin with a simple flat listing of assembly code, and as it you let it know that a certain heap allocation call is likely to be a structure, and then you just kind of let it run. So let's take a look at what that looks like. That'll work. Okay, so this is the IDA x86 emulator. My code actually is all behind the scenes, and it happens completely automatic. It just simply prompts you when you get to a heap allocation call. So we're just going to run halfway through this function. And we're going to see that it's found that there's a heap allocation call right here, actually. And it's about 20 bytes, and it's going to allocate it at this memory address. And if we want to track this heap allocation call, then you can see that later references within that heap allocation call are determined to be members of that structure. And there's another heap allocation call. So we've ran through half of this function, and we've determined that there are two structures within this code. And you can see that if you follow this into the subfunctions even, it determines all later references within the code into that allocated structure. Later on, you can see that there was a second structure allocated. I hope that's kind of visible in the audience, but there's a second structure here that was allocated, and it's passing values between the first structure and the second structure. And then finally, within the IDA database itself, of course, now this exists as a new structure. Right there. And it's determined that, in fact, one of these elements here was a word-sized value as opposed to a D word. And if we look at the code, I can pull this up real quick. You can see these two structures here. There were a couple of integer values and a short value there. So it did, in fact, determine that the value was word-sized and did correctly recognize the entire structure of both of these portions within the code. So bringing this to a close, the ability to identify arbitrary structures should really speed up binary analysis and software reversing in all areas, whether you be doing something for compatibility purposes or for vulnerability research purposes. And moving forward, I look to move into generating fuzzer templates. I hope you guys all saw Ilya's talk earlier, but depending on the type of fuzzer you use, some of them take a more structured protocol definition of basic integer size values or card pointers or whatever they may be. And if these can be determined from within the code using this emulator, those templates can be emitted quite easily, and so therefore you can automate the creation of fuzzers for arbitrary programs, whether they be proprietary or open source. And that's pretty much what I have for you. Are there any questions? No? Okay. Thank you for coming. The final thing I'd like to note is that this software will be available on labs.idefense.com, hopefully today or tomorrow. Or come see me if you like it beforehand. Thank you.